All right, guys, we're going to be going through 6.1 and we're talking about polygons. So first off here, we have a quick definition of a polygon. I'm going to be referencing this a fair amount. So what is a polygon? A polygon is defined as a closed plane figure formed by 3 or more line segments. Each segment intersects exactly 2 other segments and only at their endpoints. And no 2 segments with a common endpoint are collinear. Okay, a lot of different pieces here. As I look at this, I think I was just underlining these things by a little bit at random, but there's kind of a few parts to this definition. And what we're going to do is we're going to look at some things that are polygons and some that are not polygons, and just try to see what piece of this definition either includes or excludes these different figures that we're examining. All right, so again, polygon, here's an example of a polygon. We have 1, 2, 3, 4, 5 sides here. This is actually what we would call a pentagon, but generically we can call it a polygon. Each segment that forms the polygon is called our sides. So all of our red segments are sides that connect each of these things here, right? The endpoints of the sides, we call those the vertex or the vertexes of the polygon. So point C, point D, point E, A, B, right down there. And then a diagonal. So this green line here in the middle is called a diagonal. A diagonal is any line segment that connects one vertex to another that's not also a side. So we could go from E to B, A to D, E to C, A to C. I think those are all the possible diagonals for this figure. But the more sides our polygon has, the more possible diagonals that could be drawn. Interestingly, a triangle, which is kind of our simplest polygon, there is no diagonal in this shape because every vertex, if I try to connect it to another vertex, that's already a side, right? If I try to connect here, yeah, it's already a side. So there's no diagonals for a triangle. It's kind of interesting. When we name a polygon, what we want to do when we're naming a polygon is pick a place to start and then move around the figure. It doesn't matter if it's clockwise or counterclockwise, but we don't want to kind of skip around. So one name would be A, B, C, D, E, right? Moving around the figure, starting at A and then moving around to E. Pretty easy there. We could also do the same thing, start at D, kind of move around, D, E, A, B, C, right? Move that direction. We could go the other way too, right? We could pick some random starting letter like C and then move around the shape this way. So I guess that would be C, B, A, E, D. That would work. That's fine. A lot of times you'll see them named alphabetically, but you do want to be careful not to do something like A, B, D, C, E. This is not a valid name here. If we just try to connect those, or let me do this. I'll do it in sort of pink. You'll notice what's going on here. If I do A, B, D, C, E, that doesn't make the shape. That's kind of the simplest way that I could say it. That would not be a valid name. All right. The names of polygons. So we have this big list of names. We name a polygon generally by the number of sides that it has. So if it has 3 sides, it's a triangle, or 8 sides, it's an octagon. And then we have this kind of catch-all. If it doesn't have a special name, we just call it an n-gon. So if something has 35 sides, for instance, we would call it a 35-gon. Boring, whatever. That's just what we do. You may notice here, actually here, that we're missing 11. 11, we could call it an 11-gon. I've also seen it called an undecagon. Doesn't really matter if you have a name for it for 11, but whatever. You don't have to have these memorized, though I expect you've probably seen a lot of these names before, maybe even at like elementary school, right? For the most part, these are the shapes we're going to spend most of our time and energy on. And in fact, in this chapter, kind of the rest of the chapter is going to be all about quadrilaterals. We've already talked about triangles kind of to the extent that we can't even, it's just we're done with them, right? We know all about triangles at this point. We're going to dive into quadrilaterals here, but throughout the rest of this chapter, or this section 6.1, we're going to be looking at some more different shapes as well. All right, let's go ahead and move forward. Okay, here are some polygons. What would we call them? I got this little table here to sort of help. Feel free to pause it if you want. I'm just going to be counting sides and naming it. Well, obviously here, triangle. 3 sides, triangle. Why wouldn't we call this a trigon? Kind of like the name trigon, but triangle is the only one that has the name that sort of references the angles, so to speak. The next one here, we have 4 sides. So this one is a quadrilateral, along with this one here too, right? 4 sides. They're not congruent. I'm just counting them, right? I know those look like congruent marks. These are both quadrilaterals. Quadrilateral, quad meaning 4, lateral meaning sides, quadrilateral. We're going to study those again in the next few sections. And then here we have 1, 2, 3, 4, 5, 6 sides. We call this a hexagon. This is a strange hexagon. It's something that we would call a concave hexagon. We'll get into that in the next couple slides here. And then here we have 1, 2, 3, 4, 5. This is a pentagon. Pretty simple idea. Just keep moving forward. All right, so let's take a look at these figures. This was our pair deck slide if you were in class for this, but which part of our definitions, we have these 4 chunks, which are kind of parts of the definition. Which part of our definition would this shape right here violate? Meaning which part of our definition could we say, oh, this shape doesn't fit that, so it's not a polygon, right? Is it a closed plane figure? Well, it's certainly closed, and it's plane. It's drawn on a flat surface here, right? There's clearly an inside and an outside, and it's definitely flat. It's on a plane, so it fits that. Formed by 3 or more line segments. Ah, I see a problem here. 1 line segment, 2 line segments, curve. Curve? I think this part, I think it violates this one here. It is not formed by 3 line segments. But let's just look at the rest here. Each segment intersects exactly 2 other segments only at their endpoints. So this segment here intersects 1 segment at the endpoint. This isn't a segment. Again, it's a curve. I guess it's violating this one too. No 2 line segments with a common endpoint are collinear. I have no line segments that are collinear in this case, meaning part of the same line. Okay, I think it's just sort of safe to say that yeah, this is not okay. Part of something in here that's not really stated as our definition is we can't have curved sides at all for a polygon. Our polygon is made up of straight line segments only. So I think just being a curve is a violation enough. Right, let's go ahead and move forward here. Ooh, okay, so this is supposed to be 3-dimensional. I will just say that this is a cube. Closed plane figure. It is closed. So that's check mark. Is it a plane figure? No. This shape is 3-dimensional. It's drawn on a flat surface, but if it is an actual cube, which it is supposed to represent, it is 3-dimensional. It is not a flat plane figure. So violates that for sure. Formed by 3 or more line segments. There's tons of line segments here. It's fine. Each segment intersects exactly 2 other segments only at their endpoints. Ah, problem. Let's just look at one of our segments. Let's look at this one right here. This segment has 2 endpoints where it touches a bunch of other lines, right? It touches, I'll number them here in sort of blue. So it touches 1, 2, 3, 4. Each segment intersects exactly 2 other segments. This red segment intersects 4 other segments at their endpoint. So definitely violates that part as well. No 2 segments with a common endpoint are collinear. I think we're okay there, but it definitely violates this part and this part for sure. All right, let's go ahead and move forward. All right, convex versus concave. These are some descriptors that we can give of a polygon. So a polygon is considered concave if any part of a diagonal contains points that are in the exterior of the polygon. Here in this dotted line, we can see here is a diagonal. It connects these two vertices. This vertex over here, this vertex over here. This is our diagonal. Exterior, it's on the outside, right? This is the inside here. This is the outside. This diagonal contains points of the exterior, so we call this concave. Another thing people like to think about concave figures is sort of being caved in. It's almost like it got punched in, right? This indentation in the shape is concave. Convex is the opposite of that. So the diagonals of a convex polygon do not contain any points that are on the exterior, in the exterior. All the diagonals of this shape are inside totally, right? We can't connect two vertices on the outside, not with a straight line, with like a curve or something we could, but all of our diagonals, this is all of them in this particular shape, are on the inside, and we so call this convex. Another thing about these two particular descriptors are with the angles as well. So the interior angles, so for a convex shape, all interior angles are less than 180. So all of these, 1, 2, 3, 4, all 4 of those angles are less than 180. If it's concave, at least one, this one right here, will be greater than 180. So at least one interior angle greater than 180. That was very sloppy writing, but hopefully you heard the words as well. One interior angle, right? This is more than a straight line. This angle here passes more than a straight line, right? There's more. You can sort of see that there. All right, cool. Let's go ahead and move forward. So let's go ahead and, again, this was a Pear Deck slide. So which of these shapes are convex? So I'm going to go through and show which ones are concave. That's kind of easy. For those, we can either look at the interior angles, see if there are any interior angles that are greater than 180, or we can find diagonals that are on the outside. Both of those would identify them as concave, so we could eliminate them. Here we have, right, diagonal on the outside. This one is not convex. Again, diagonal on the outside, not convex. Diagonal on the outside, not convex. Diagonal on the outside, not convex. Diagonal on the outside, again, not convex. So again, that's one way to do it. We could have also looked at the angles here to help a little bit, right? This angle greater than 180, this angle greater than 180, this angle here greater than 180, this one here greater than 180, this angle here greater than 180. All of those would have identified these as concave. So all the ones with X's are concave. The remaining shapes, number 2, 4, 6, and 8, are all convex. Let's just take one and sort of look at it. All the interior angles are less than 180. When I go ahead and try to draw my diagonals, every diagonal that I want to go ahead and draw is inside of the shape. So I drew all the diagonals and they're all on the inside. So you can see how that works kind of either way. Examining the angles, making sure they're all less than 180, or looking at the diagonals. Regular versus irregular. So this is another descriptor that we can give of our polygons. So a regular polygon is equiangular and equilateral. So all the angles are equal, all the sides are equal. If it doesn't have both of these characteristics, we call it irregular. Pretty simple idea. We're familiar with a lot of regular polygons. Usually when you think of hexagon or octagon, you think of regular polygon, right? In fact, let me just go ahead and draw a regular octagon, or at least my best ability to do it. Hopefully it sticks out to you as something that you recognize. So here, it's pretty bad. I think this isn't going to work, but that's okay. We will do our best. So here is my best idea of a regular octagon. What does it look like? Looks like a stop sign. right? Stop. Anyway, we're familiar with regular polygons. They kind of show up all over the place. We've probably seen more regular polygons than irregular polygons, I would hazard to guess. Though that does bring me up to one point here. This is a pretty normal shape, right? You probably looking at it, you can say, yeah, this is a rectangle. Rectangle is not regular. It has all right angles. So it is actually equiangular, but these sides are equal and these sides are equal, but it's not equilateral. Not all the sides are equal. So this is actually irregular. Even though it is a pretty normal shape, it's still irregular, geometrically speaking. Which polygon below is regular? Well, we can eliminate that rectangle right off, right? This one right here, not going to be this one, not equilateral. I'm also going to eliminate another one that's a little tricky. So C is not regular either. It is equilateral. All the sides are equal, but the only angles that are marked are these ones here. These are also angles, and they are different than these other ones. So it is not equiangular. So it's not this one. It is this hexagon here. 1, 2, 3, 4, 5, 6. All the sides are the same, and all of the interior angles are the same. So the hexagon here in the middle is a regular hexagon. Regular hexagon. As an aside, if a shape is regular, it will also be convex. And this one, obviously not convex. If it is regular, it will also be convex. All right, now we have the polygon angle sum theorem. All right, so this is just like our triangle sum theorem, but we're extending it to all polygons. So we all hopefully know that triangles always add up to 180. All the interior angles of a triangle add up to 180. Well, every polygon has a set sum like that. Every convex polygon has a set sum like that. And we can figure them out using this formula right here. So n minus 2 times 180, where n is the number of sides. Let's go ahead and just use it really quick. What is the interior angle sum of a pentagon? So a pentagon has 5 sides. So if we use our formula, that's 5 minus 2 times 180. That's 3 times 180, which is equal to 540. So all pentagons will have their interior angles add up to 540. But why? Why? Okay, here's the reason. I'm not going to get into the depths of this, but let's just draw some random pentagon. And here's a random pentagon. It's not regular, it's just random. It has to do with the fact that every shape can be, from a single vertex, be divided into triangles strategically by drawing some diagonals. So here and here. I have taken this shape, which is a pentagon, and I've divided it into 1, 2, 3 triangles. I know that 3 triangles are 3 times 180. So the angles of these 3 triangles will add up to 180 each, so 3 times 180. And all of the angles that I have here, if I look at them, all of the angles of my triangles and the angles of my polygon, of the pentagon that I have there, all match up. So every angle in a triangle, if I add those all together, they also match all the interior angles of my pentagon. So I end up getting the same thing. So that worked for a pentagon. Let's just quickly look at just another shape. Let's go with more sides. Let's go with a hexagon. 1, 2, 3, 5, 6. It has to do with, it doesn't matter where I draw my vertex, that when I have a hexagon, so a pentagon, I was able to split it into 3 triangles. This hexagon, I'm going to be able to split it into 4 triangles. I will always be able to split my figure into 2 less triangles than there are sides. And those triangles all add up to 180. So that's where I get this formula, n minus 2 times 180, right? Hexagon, 4 triangles, 4 times 180. We're going to add up to 720 in a hexagon because there are 4 triangles, and that's 4 times 180. It's a cool formula, and you could kind of play around with this and look and see how this works for basically every shape. No matter how many number of sides you have, you'll be able to split it into 2 less triangles, n minus 2. Multiply that by 180 because triangles are 180. There you go. You get your sum formula. And again, it's going to be easier for us to kind of remember this formula than memorize each individual shape, right? We'll probably eventually memorize that, say, a pentagon is 540 if we do enough pentagons, or that quadrilaterals are 360. That's actually one we probably will remember because this chapter we're going to focus on those shapes. But it's going to be better for us just to kind of memorize this formula and use it when we need. All right. The next theorem is about the exterior angles of a polygon. So the exterior angles are found by extending the side. So we take one of our sides here and we extend it. So here, exterior angle right there, we extended it out. And the angle that's on the outside of the figure is called an exterior angle. It is always going to be supplementary to the interior angle because we're just creating it by extending a side. So it's always going to be a linear pair with the interior angle. And it's always going to be, the sum of these angles will always be 360. It doesn't matter what type of polygon we have. It could be a triangle or a pentagon or an octagon or a 35gon. It doesn't matter how many sides. These angles on the outside, if we make all of them, will add up to 360. It's a cool property, really useful for us to solve things. It's also going to be really useful for us to sort of figure out the interior angles kind of in a backwards way, because if we find the exterior angles, we can just find the interior because they're supplementary, right? So if I know this one was 180, or sorry, 81, and I know these add up to 180, that means this one over here has to be 99, right? So if I know the exterior, I can actually kind of find the interior. And so this sum can kind of help us do that as well. If we remember that relationship, that interior angles and exterior angles are supplementary. All right, here is a warm-up for the second part here. So we have a quadrilateral. So feel free to take a moment and kind of try to solve this problem on your own if you want, but pause it if you want. I'm going to go ahead and do it myself. So we have a quadrilateral. So 1, 2, 3, 4 sides. We can use our interior angle sum formula here to figure out what the sum will be. 4 minus 2 times 180. That's 2 times 180. So the interior angles here are going to add up to 360. That's true for all quadrilaterals. So that's actually probably something we will memorize eventually. That makes this a pretty simple problem to solve for x. We just want to add up all of these interior angles, all 4 of them. And they will equal 360. So kind of a long equation, but not very difficult to solve. From here, we want to combine like terms. So we end up with 3x plus 22 plus 27 plus 71 minus 9. So those add up to 111 equals 360. Then we subtract 111. 3x equals 249. And then we divide by 3. So we get that x equals 83. So x is 83. And from there, we can actually find all the different angle measurements. This one would be 83 plus 22, which is 105. Angle L would be 83 minus 9, which is 74. And then angle M would be 83 plus 27, which is 110. Pretty simple to then find all these measurements. We could just double check that this works, right? make sure that those do all add up to 360, but I feel good about it. So we'll go ahead and move on. All right, so here is an example of using some of the properties that we just talked about. Let's kind of read the information and see if we can come up with it. So what is the measure of each interior angle in a regular decagon? Okay, regular decagon means 10 sides and angles, right? It always, polygons are always going to have the same number of sides and angles. Triangles have 3 sides, 3 angles. Quadrilaterals have 4 sides, 4 angles, right? And so forth. So each angle is going to be the same because it is regular. So all angles will be the same. There are a couple ways that we can go about this. So I'm going to show one method here. And this one I think will be the most intuitive. Let's figure out what the sum is. What is the sum for a decagon? 10 minus 2 times 180. That's 8 times 180. So it's going to be 1,440 degrees. So all of the angles of a regular decagon will add up to this. Doesn't matter if it's regular, but in this case it is. They will always add up to 1,440 degrees. Well, if there are 10 of them and they are all equal, I can just simply divide this by 10. 1,440 divided by 10, 144. So each angle, all 10 angles will all be 144 degrees each. Pretty simple. This is kind of the most straightforward way to have solved this problem. The other way to have solved this problem is to actually use the exterior angles. And so let's say we have a polygon, it's a decagon, or a regular decagon. If we extend our sides out, we can figure out what the outside angle is. Well, just like this, there's going to be 10 sides and 10 interior angles. There will also be 10 exterior angles. There will also be 10 exterior angles. And if it's regular, if the interior angles are all the same, the exterior angles will all be the same. So there's going to be 10 equal exterior angles. We know no matter what polygon, the exterior angles will add up to 360. Divide that by 10. That means each exterior angle is 36 degrees. Each exterior angle is a linear pair with each interior angle. 180 minus 36 gives me 144. I could figure this out this way as well. Two approaches. This second way, the one in red, is kind of more advanced, a little trickier, not quite as direct as what I was doing on the first one, but both of them ended up with the correct answer, 144. Sometimes we may not be able to do this more direct method, so we want to always sort of keep this thought in our back pocket and remember the connection between the exterior angles and the interior angles, and how the exterior angle sum may actually be able to help us find information about the interior angles. All right, what is the value of z? Okay, so here we have a bunch of interior angles. 1, 2, 3, 4, 5. There's 5 of them, which means this is a pentagon, right? Okay, pentagon. We learned previously, or we solved previously, that the sum here is actually going to be 540. But if you don't remember that, 5 minus 2 times 180. It's fine that you don't remember it. Just do a quick calculation. You'll end up with the same thing. And we're going to use that to set up and solve an equation. I just need to add these 5 angles together. 4z plus 5z plus 3z plus 5z. I suppose I could have combined like terms kind of ahead of this. Equals 540. I'm going to put that on this side since that's where I have a little space. Okay. Okay, so that's 4, 9, 12, 17, 20. So I get 540 equals 20z. I think I could have just combined them beforehand since it was relatively easy, but that doesn't matter. Divide by 20. That's 54 divided by 2, so that's 27. Pretty easy, not too bad. we always need to be able to kind of quickly apply this formula whenever we need. And make sure we have all of the angles in here. There may be times where we don't know all of the interior angles and we can't kind of take this approach, but there we were fine. Right? And one more example here. Example 3. If the exterior angle of a regular polygon is 60 degrees, how many sides does it have and what would we call it? All right. Exterior angle is 60 degrees. Let's just sort of sketch. We don't know how many sides this is, but we're going to say that we have an exterior angle. So this out here is our exterior angle. Sorry, 60. That means that the interior one would be 120 because they are always, this is the interior of our polygon. Again, we don't know how many sides this thing has, but that's the interior angle. And we always know that relationship. So we have a couple approaches here. We could figure out what polygon has an interior angle of 120. It is important that it is regular. If it wasn't regular, that could be any polygon, right? We could even have a triangle with an interior angle of 120, or we could have a octagon or quadrilateral, or all kinds of things. But since it's regular, all the angles are 120. So we could sort of figure that out by kind of guessing and checking. We could say, I don't know, maybe it's a hexagon or an octagon and do our calculations and see what happens. But I don't think that's the best way to go about it. What instead is, let's think about the exterior angle. So if we know the exterior angle here is 60, however many we have, we know they have to each be 60 because they're each supplementary to the interior angle, which are all the same in a regular polygon. And we do know that when I add them all together, they have to equal 360. So I have n exterior angles, which matches my number of sides. The exterior angles will match the number of sides. And I know they need to all add together to be 360. So I have 60 plus 60 plus some number of 60s, n of them, and they're going to equal 360. Well, I can represent this. This is just repeated addition n times. So I can repeat this. I can say it's 60n equals 360. I can represent that with just multiplication. If there's n of them, I multiply it by n. That's what that sum would be. And this just becomes a simple formula now. Divide by 60. I figure out that n equals 6. So this is a 6-sided figure, which makes it a hexagon. 6-sided figure makes it a hexagon. There we go. Go ahead and clear this. All right, so here were some problems where I was going to have you do very similar ones to our examples. Again, feel free to pause at any point. This one's just like example 1. So it says, what is the measure of each interior angle of a regular octagon? Okay, octagon has 8 sides, right? 8 sides. Also 8 angles, right? That's because we really are working with the angles here. Let's find the angle sum. So let's say 8 minus 2 times 180. That is 6 times 180, which is 1,080 degrees, or 1080. 1,080 degrees. Since I know there are 8 of them, I just simply divide it by 8 because that's what we're going to do. There are 8 congruent angles, so divide this by 8. We figure out that each angle is exactly 135 degrees in an octagon. So there we go. That was, again, our direct method. It's a totally fine method, not too bad. Remember, there was another way to do this with our exterior angles, right? For an octagon, I'm not going to draw an octagon, but let's just assume, whatever, it doesn't matter. I'll draw something of an octagon. It's not perfectly regular, but we could figure out this exterior angle very easily. There are 8 of them. They're all equal. 360 divided by 8. All of the exterior angles of every polygon add to 360. Doesn't matter how many sides. So 360 divided by 8 means that each exterior angle is 45 degrees. The interior angles are supplementary with the exterior angles. 180 minus 45 gives me 135. 135. Same answer. Different approach, same answer. Again, sometimes one of these ways might be a little bit easier to approach a particular problem, whether we think about solving with the exterior angles to help us figure out the interior, or the interior to help us find the exterior. Again, both methods are valid. All right, question 2. Here's another one. Again, feel free to pause it if you want to solve this. Here we have a quadrilateral. There's 4 sides here. If we don't remember, the sum here should be 360. We could use our formula to just double check that, but that would give us the same value. So there we go. So we can set up a nice equation that lets us solve for x, a pretty simple one. We just add all these angles together. And they equal 360. Be careful, make sure you do appropriately count the number of sides. I see a lot of people mistakenly think, they look at it and they don't actually count the number of sides, and they get it wrong, right? They set up the wrong equation based on what the angles are supposed to add up to be. So just be careful with that. Combining like terms here, we have 2x equals plus 237 equals 360, and then we have to subtract 237 from both sides, which gives us 2x equals 123, and then we'll divide by 2, and x is 61.5. So this one would be 61.5. This one would be 58.5, yeah, minus 3. So there we go, got the answers. I mean, this is all we were supposed to do, but took it a step further to find particular angle measurements. That's something we may need to do when we're solving problems. All right, and then the last one for you guys to do here, you can pause it if you want to do it ahead, but we have a regular polygon. Again, we don't know how many sides it has, but the exterior angle here, this one on the outside, is 30 degrees. That means the one on the inside is 150, and that may be helpful, it may be not. I'm going to take an exterior angle approach. How many sides would this polygon have? Again, it is regular, so all of the exterior angles will be the same, and all of the interior angles will be the same. And we know there's going to be n exterior angles, which matches the number of sides. So 30 degrees times n is going to equal 360. This is a pretty easy approach to take. We divide by 30, divide by 30. That's 36 over 3 is 12. So 12-sided, we call that a dodecagon. Dodecagon. There we go. Let's go ahead and move forward just to kind of summarize this. So we're talking about kind of lots of different polygons here. In the rest of the chapter, we're going to be focusing on this side over here, all of the different quadrilaterals that can exist. But throughout this chapter, we'll kind of make use of all of these different things. Here's a last challenge problem. Kind of an interesting one. I didn't actually get to this in class, but I'll go ahead and go through it here. So it says, find the name of a polygon whose interior angle measure has a sum of 2,520. We could just sort of do a guess and check to do that, or we could actually just solve it. So solving is the easiest, right? We can solve for n, for the number of sides. There we go. We wrote the equation here. The interior angle sum equals this number. So we just simply divide by 180 to get rid of that. So we have n minus 2 equals, using my calculator here, 14. So n minus 2 equals 14. Add 2 to both sides. I figure out that n is actually 16. So a 16-sided shape, we would call it a 16gon. Nice fun name, but a 16gon would have that particular angle sum. It is sort of helpful to remember, just kind of in general, a couple things that are going on. As the number of sides increase, the angle sum keeps going up. It keeps going up by 180, multiples of 180. So the more sides we have, the larger the interior sum is going to be. Also, the bigger the interior angles are going to be, right? They're going to keep getting bigger and bigger and bigger as well. But the exterior angles, since the interior angles are getting bigger, the exteriors are actually going to be getting smaller because those are supplementary to each other. So keeping that relationship in mind can kind of help you think about these problems well as well. All right, and here's the homework for 6.1. Remember to turn these two assignments into Google Classroom, number 26 and 30. All right, see you guys later.